Okay, so I need to give you a few examples of uh, checking linearity, right? So let us check a system which only shifts an input signal. Let's say there is a system and it shifts an input signal by some amount A, right? So we can say that, okay, if the input signal is X, the output signal is X of, yeah, box minus A. So we need to do that. Um, so how do I go about it? So first I need to check superposition, right? Superposition. So superposition requires that, okay, if x1 is any signal, so it will be mapped to x1 of, yeah, box minus A. If x2 is another signal, it will be mapped to x2 box minus A. A can be any value, right? And now I need to check whether x1 plus x2. So now x1 plus x2. The shift doesn't care about this plus, right? It will simply apply the shift to, because x1 plus x2 means that at any point in time you will have to first calculate x1, that will give you x1 of t, then it will, you calculate x2 of t, and then add the two. So basically, if there was no shift, you will simply have a box, yeah? x1 will map to x1 and x2 will map to x2. But this will only be if there was no shift. Because there is a shift, so you will have to apply the shift, and you can see that this is just the sum of all those two signals. So superposition is automatically um, satisfied. The second property which we need to check is that if x is mapped to x of delta minus box minus a, and now I scale this, and the scaling has to be amplitude scaling, not time scaling. So let's multiply this by some number k. K can be any real number, right, or complex number, even complex number, doesn't matter. So you can see that now the shift will apply to k times x. Now k does not have any time dependency, so it will simply be k times x of delta. So it is so simple that you don't even notice. Yeah. I mean, to make this explicit, it looks like you need to have an explicit thing. So let's call this y1, right? Let's call this y1, huh? Including this transformation. Let's call this y2. So you can see that this is actually y1 and this is y2, and you have y1 plus y2, right? Similarly, I can call this as y. So now you can see that this is k times y. Yeah, so it's obvious. This was very easy. Let's complicate this a little bit. Let's consider a system which maps x to y, and instead of writing the system here, um, we I'm just writing an equation, yeah, because sometimes things are not easy to write in such a small box. So let's write this. Let's say I have the derivative operator which applies to y, right? And then I have some constant a times y, and let's say this is equal to some constant b times the input. And let's say x is the input. Yeah, so x is the input, y is the output, and the equation dictates how x will be mapped to y. So now superposition. How do I go about superposition? So I will say, okay, if this is x1 and this maps to y1, so y1 has to respect this equation. dy1 plus ay1 equals bx1. Yeah, this is the meaning of this mapping. Yeah, let's say x2 maps to y2, so that is only possible if these two satisfy this equation. So I write this same equation, but this time with x2 and y2. Yeah, this is what is meant by these two mappings. So now I need to check, yeah, how is this sum mapped. Yeah, so now I need to check that. So let's apply, instead of x, I need to apply x1 plus x2, right? B. Now, but I cannot actually write this, I cannot say y1 plus y2 because I don't have any proof. I will have to show that the left hand side is still as if I'm adding. So now, look at this, b times x1 plus x2. So what if I add these two? If I add these two equations, I can take b common and I will have this thing. So it's the same as if I'm adding the two equations. So I don't care whether the system is linear or not. If I'm adding these two things, I will add these two things as well. And what will happen? When I add these two things, automatically A will become common and D applies to y1 plus y2. So you see, it automatically satisfies superposition, superposition, superposition. Now uh, let's try homogeneity, right? So homogeneity will require that, let's say x maps to y, so it means this equation, and I want to know what happens to k times x. Yeah? So now I want to know what happens if x is replaced with k times x. Yeah. So now I want to show that I get something on this side similar to as if it was k. So I need to show that it has to be k times y. This is to be shown, the question mark. So now, how do I go from bx to kx? So let's say I start with bx, so b comes here, x comes here, and I'm writing this k from my side. So I have actually multiplied the right hand side by k. I'm multiplying the right hand side by k. I have to do the same on the left side. So it will be k times, so k times ay plus k times dy. I can rearrange this in such a way that d of ky plus a times ky as b of kx. So you see, kx maps to ky. So it's very easy, right? Very easy, but do not try this. This is okay. What is not acceptable is that if you do something like this, let x of t is, for example, unit step, yeah, and then you prove it, because then you will be proving it only for a particular signal. That is not a proof. A proof has to be for all possible signals, right? Yeah.